Okay, hey, welcome back. This is 5.8. We're still working with integration. In particular, we want the integrals of some inverse trig functions. So first, just recall the derivatives of some inverse trig functions. And from there, we should be able to get the integrals. So the two main important ones that I expect you to have memorized, the integral of tan inverse, or if you want arctan, is 1 over 1 plus x squared. The derivative with respect to x of sine inverse, or arcsine, if you would rather, is going to be 1 over the square root of 1 minus x squared. Those are the two main important ones. Cosine inverse is just the negative of this, and cotan inverse is just the negative of this. The secant ones are a little more complicated, but from here we can just reverse the process and have our integrals. So let's introduce those integrals. So the two that I want you to have memorized are the ones for arcsine and the one for arctan. So the integral of du all over the square root of a squared minus u squared is our arcsine. Okay, so that would be sine inverse, if you wish, of u all over a plus c. And the other one we need to memorize, du all over a squared plus u squared. A is a constant and u is the variable part, in case you're wondering. That's going to be 1 all over a tan inverse of u all over a plus c. So please memorize these guys, as well as those derivatives. The third one I don't need you to memorize. Du all over u times the square root of u squared minus a squared. And that will be 1 all over a times secant, or secant inverse, if you'd rather, of the absolute value of u all over a plus c. So it's a little more annoying, and I'm not going to expect you to memorize it. Okay, let's look at some examples here of applying this problem. Okay, so example 1, for a, we have dx, the integral of dx all over the square root 4 minus x squared. So putting it into the form, if you wish, u is just x, or x is u, if you'd rather. Du is just dx. So there's really nothing to do there. You could just pretend u is x and integrate away. The a value is not 4, it's 2, right? A squared is 4. So we could just plug and chug into our formula, sine inverse of u, which is just x, all over a, which is 2, plus c. Part B is a little more complicated. So we have dx all over 2 plus 9x squared. That is an arctan form, right? It doesn't have the square root. That's the big red flag for us. So this time we'll let the u actually equal 3x, right? Because u squared would be the 9x squared. So our du will be 3 dx. In other words, dx will be du over 3. And then on top of that, our a value is not 2, it's rather square root 2. Right? Okay, so let's see what we got. Do some subbing here first to get it in terms of du. So I have dx is du over 3. Let me put that to the side rather than. So I have 1 all over 2 plus u squared times dx, which is now du over 3. I could factor out that constant of 1/3, and then I just have the integral of du, and it's kind of now in the form of the template that we're memorizing. Right? So I can go ahead and integrate. It'll be 1/3 times 1 over a, which is root 2, times tan inverse of u over a. And again, a is root 2. And then plus c, and then back sub, and we should be done. 1 over 3 root 2, arctan, or tan inverse of 3x over root 2, plus c, which should be the answer. Yep. Let's look at one that's the arcsecant type. C. The integral of dx all over x times the square root of 4x squared minus 9. So again, to get it into kind of the template form, I'm going to have to redefine u as 2x. So du will be 2dx, and dx will be du over 2. The a value will be 3. And we're going to need to rewrite the x in the denominator using this equation here. So x will be u all over 2. So it's kind of our material box. So my integral, then I'm going to push the dx back there. So I'm replacing x with u over 2. 1 over u over 2 is the same as 2 over u. So I'm going to write it as 2 over u. And the square root of u squared minus 9, and then times our dx, which is now du all over 2. So there's some nice cancellation there, and we just have the form du all over u square root u squared minus 9. And of course we could go to our inverse secant form. So is that going to be 1 over a? Yeah, so it's kind of like the tan, except with that absolute value in it. So 1 all over a is 3. The secant inverse of absolute value of u all over 3, and then plus c. So back subbing 1/3 secant inverse absolute value of 2x, which is the same as 2 absolute value of x if you'd rather, but I'll just put absolute value of 2x over 3 plus c. Okie dokie. Sometimes they'll throw, instead of just having to do u as 2x, so some version, every once in a while they'll put a function in there for u. Okay, so that's what's happening here in example 2. So let's take a look at that guy. The integral of dx all over the square root of e to the 2x minus 1. So it certainly looks like maybe a secant inverse, but we're just missing that factor in front of the square root. But if you let u equal the e to the x, because e to the 2x you could really think of as e to the x squared, right? So this would be e to the x squared. And that, then we'll make that our u squared, and the a will be 1, right? So anyways, du is e to the x, u is e to the x, du is e to the x dx, and then dx will be du all over e to the x. Okay. So doing our substitutions here, I'll have du all over an e to the x, I can put that in the denominator then, and then square root of u squared minus 1. It seems like we're in trouble because I haven't gotten rid of that e to the x, but you could replace it with u, right? The first line of our box of substitution stuff says that e to the x is just u, so I could rewrite it as du all over u times the square root of u squared minus 1. And then it definitely has the arcsecant form. So we'll go 1 all over a. In this case, a is 1, so it's just 1. And then secant inverse of the absolute value of u all over a plus your integration constant. And then, of course, that's just going to be secant inverse of the absolute value. E to the x is positive, so you can just write u to the x and then plus c. Good stuff. This one, yeah, so sometimes you got to split them into 2 integrals. So example 3, you have the integral of x plus 3 all over the square root of 4 minus x squared dx. So right off the bat, there's not much you could do. It's that numerator, you can only have one term in the numerator for it to be in the appropriate, I guess this would be like a sine inverse form. So what you're going to do is butterfly it. You know, there's one integral, there's your second integral, And so what do you get? You get x all over the square root of 4 minus x squared. That'll require a u sub, and then plus the integral of 3 dx all over the square root of 4 minus x squared, and that's just an arc sine. Okay? So in the first guy, you need a u sub for 4 minus x squared. Du be negative 2x dx, and then dx is negative du all over 2x. Okay? So my first integral becomes x all over the square root of u times negative du over 2x. For the second integral, you note that u is just going to be x, so du is dx, and then I guess a is 2. Okay. You can go straight to integrating it if you want. That's probably what I'm going to do. So plus there's a constant of 3 floating around, and then it will be sine inverse of u all over a. In this case, u is just x all over a, which is 2. Let's see. And then let's clean up that first integral, so you can pop out a factor of negative 1/2. The x's are gone. Let's rewrite the 1 over square root u as u to the negative 1/2. And then power rule, so u to the negative 1/2 plus 1 is u to the 1/2. Divided by 1/2 is the same as multiplying by the reciprocal of 1/2, which is 2 over 1. And plus 3 sine inverse of x over 2. Let's see. And then we can start back subbing. So negative square root of 4 minus x squared plus 3 sine inverse of x over 2 plus c. Okay. Whoops, I screwed up somewhere. Well, it should have been 2. I wrote it as 3. Yeah, no big deal. Same answer. Okie dokie. Let's see what else they got for us. Problems where you have to complete the square. So just a reminder of completing the square. I don't know if I was section 1, so I guess we'll call this section 2. Completing the square. So just a reminder, if you have something like x squared plus 3x, I don't know, the way you would see it back in algebra, maybe equals 5. In order to complete the square, you have to add in the b value all over 2 squared. So in this case, it would be like 3 all over 2 squared. It should be, unfortunately, 9/4. So you would go x squared plus 3x plus 9/4 equals 5 plus 9/4. And then you can factor that. X plus 3/2 squared equals, what is this, 29/4. And then you can solve for x by doing the square root property. You really had to have a leading coefficient of 1 in order to pull this off. So if you had something like 4x squared plus 2x, let's not make it so nasty, plus 8x equals 5. In order to complete the square this time, you'd have to factor out the 4. So you'd have x squared plus 2x. And then you're going to add something in here. But when you add that something to the other side, it has to be 4 times that something, right? So 2 over, the number you would do is 2 over 2 squared here, which would just be 1. But you're not adding 1 on the other side, you have to add 4, right? So it would be x plus 1 squared equals 9, and then you could solve for x. Anyways, that's kind of, I think, where you saw it back in pre-algebra or algebra. For here, for us, it's a little bit different. What they want you to do is we'll have, so in example 4, you have the integral of dx all over x squared minus 4x plus 7, right? So you're going to kind of associate these two guys together and complete the square on that. And then instead of adding something to both sides, you add it in and then immediately subtract it. You kind of see that's what they do over here. in their explanation stuff. Okay, so that's what I'm going to do. I have the integral of dx all over x squared minus 4x plus 4 over 2 squared. So 4 over 2 is 2, 2 squared is 4, but then you have to immediately subtract it. Okay? But in doing this, you're going to be able to factor the first portion into x minus 2 squared, and then you have minus 4 plus 7 is plus 3, and now it has the form of the inverse tangent where our u value is x minus 2, so our du is dx, and then our a value is square root 3. Okay. So we can do our subs and put it into kind of our template form. So dx is just du all over u squared plus 3, and then 1 all over a, 1 over square root 3 tan inverse of u all over square root 3 plus c, and then we can back sub. Right? So it would be 1 all over square root 3 tan inverse of x minus 2 all over square root 3, and then plus c. Okay, so that's all there is to that. Here's another one, example 5. So we want to find the area of the region bounded by this f of x and these two lines. They give you a picture down here. So you're integrating from 3/2 to 9/4. So here I go. So 3/2 to 9/4. And our function 1 all over the square root of 3x minus x squared dx. So it kind of looks like an inverse sine. Okie dokie. I really like to rewrite it with a leading coefficient of 1 when I complete my square. So I'm going to rewrite that denominator a little bit to pull that off. So the way I do it is to factor a negative out, and I'll have x squared minus 3x, and then I have to add something in to complete the square. And then I would normally immediately subtract it, but because there's this negative out here, I'm really needing to add it. Okay, so plus blank. And so what is it? I need to take the b value, which is negative 3 over 2, and then square it. So I'm going to have 1 all over the square root of negative x squared minus 3x plus 9/4, and then plus 9/4 again. And then I lost my dx. And then I'm going to rearrange the terms using the commutative law of addition as 9/4 minus the x squared minus 3x plus 9/4, which you could rewrite by factoring into x minus 3/2 squared. And you see, yeah, that's an inverse tan where our u is the x minus 3/2, so du is just dx. And then our a value is 3/2. Okay, you should be able to just sub and go. So dx is du over the square root of 9/4 minus u squared. So that will be sine inverse of u all over a. So 1 over 3/2 is the same as 1 over 3 over 2 is 2/3, right? Plus c, and then back sub the u value. So we have sine inverse of 2 times x minus 3/2 all over 3. C, you can distribute the 2 and get rid of the ugly complex fractions. 2x minus 3 all over 3 c. Whoops, and we're evaluating, so it's not plus c. Never write the plus c if you're evaluating. It'll make you look like a freshman. So I need to evaluate, and we're going from 3/2 to 9/4. Okay. Maybe I should have left it as a fraction. I don't know. Too late. Anyway, sine inverse of 2 times 9/4 is really 9/2, and then minus 3 is really 6/2 all over 3, minus sine inverse of 2 times 3 halves is really 3 minus 3 all over 3, so that would be 0. So sine inverse of 3 halves all over 3 is the same as 1/2. And then minus sine inverse of 0. And of course, sine inverse, how is that from negative pi over 2 to pi over 2? So the first guy is pi over 6, and then minus 0. So it's just pi over 6. Okay, let's see if they have anything else for us. Review of basic integration. So we know a lot of integrals now. You're going to be able to do that. And then they do some comparisons, so don't be fooled type deals. You know, it'll just come down to your basic familiarity with things. Some integrals we're still not able to do at this point. So part C, it says, you know, we can't, at this point, we don't even know how to integrate part C. And then they do some more comparison of integrals. That's about it. Yeah. Yeah. Let's try at least do 1 from the homework, right? Looks like number 10 is a complete the square problem. Let's try number 11. The integral of x all over x to the 4th plus 2x squared plus 2. Looks like I should be able to complete the square on that in a weird sort of way. Ugh, that looks annoying. All right, so let's try it. So I got x dx all over x to the 4th plus 2x squared plus blank minus blank plus 2. 2 all over 2 squared is 1, so minus 1 plus 2. If it doesn't work, we could just, you know, try something else. No big deal. Sometimes it's a trial and error process. So we got x squared plus 1 squared plus 1. Okay. So yeah, I think our u value is the x squared plus 1. And then I'll have a du is 2x dx. And then dx is du over 2x. And our a value is 1, of course. So the integral of x all over u squared plus 1 times our dx, which is now du over 2x, backdrop of 1/2. X's nicely cancel. And du over u squared plus 1, which is an inverse tan. So we get 1/2 times 1 over a, which is 1, times tan inverse of u over a, again a is 1, plus c. So we get 1/2 tan inverse of x squared plus 1 plus c. Let's see if that works. 1/2. See if those trig functions. Tan inverse of x, oops, x squared plus 1, and then more capital C. Yay. Okay, I think that should probably do us for this section. There'll be some challenging integrals there for you, but you can handle it. Okay. Thank you for watching as usual, and we will see you next time.